Hi, my name is Jesus Alfonso Robles and I am a senior in electrical and computer engineering.
Hi guys, I'm Benjamin Ribble and I'm doing mechanical engineering.
Hello, my name is Mitchell DeZurich and I'm a computer engineer.
Hello, my name is Ajay Katoch and I'm a computer engineer.
Hi, my name is Jared Caswell and I'm the systems engineer.
Hey, I'm Lena Wojtek. I'm a double major in electrical engineering and computer science, and I am the project lead for Team 19074, Secure Video Transmission over a Cellular Network. Over the past year, we have developed a system for General Dynamics that allows one to control and automate a drone anywhere in the world using LTE cell service, both over commercial and private networks.
This project uses a novel approach to controlling UAVs, which brings a drone and its controller together via the cloud. The connection uses military-grade encryption to block commands and video data from the outside world. An onboard microcontroller collects video and flight data and sends it to the user while also forwarding commands to the flight controller. In case of emergency or loss of connection, the microcontroller takes over and autonomously brings the drone to safety.
A UAV controlled over LTE has many purposes in the many fields General Dynamics Mission Systems is a part of. One example of this is disaster relief. To help first responders in hazardous situations, GD can set up a temporary secure LTE network for drones to communicate in. The UAVs can then be released and deliver crucial supplies to those in need and help find those who are lost. The camera and onboard sensors, combined with the essentially limitless range, make the drone a very useful tool in many areas. In terms of physical supplies, only one subsystem contains physical parts, and that is the drone subsystem. The materials that were utilized in this project center around the Terret T680 Pro and X6 drone frames. Featured in the frames are motors and speed controllers, microcontrollers, PPM encoders, sensors, batteries, flight controllers, and the wires that connect and couple these components with each other.
As mentioned previously, this methodology is centered around three subsystems. The three subsystems are the following: the drone, the ground control station, and the server. This project is one of the first at the University of Arizona to incorporate the Agile methodology for senior design. This differs from the traditional method as the Agile section focuses on what we like to call the MVP, or the minimum viable product. The MVP for Team 19074 centered around the requirements of encrypting all communications between the three subsystems. As the project progressed, the MVP was achieved by CDR, and the MVP shifted to the flight requirements. Getting the drone to fly proved much more difficult than expected due to issues with the flight controller not working properly. After overcoming that challenge, the drone had a successful flight that was showcased during ISR. The Agile methodology is mentioned as the method where you want to fail the fastest. This allows us to explore more risky avenues that may not work and back out of that avenue before too much development has been put into it. This method will produce a better product in the end and will help eliminate key issues before they are too costly to fix.
As stated, using Agile methodology, three subsystems were produced: the drone, the web server, and the ground control station. Although the drone is the only physical component and the centerpiece of the project, nothing would be complete without the other two. The web server is the backbone of communication for the UAV LTE system. Although hidden in obscurity by the cloud, it plays an essential role in allowing a control station and a UAV to interface with each other. The server acts as a static, known location that the dynamic drone can contact to broadcast their status. Meanwhile, users can go to the URL or IP address associated with the server to access the contents of the web app. Once connected, the server can provide users with information on what drones are available and connect them to one. It then relays control information from the user to the UAV and returns video, GPS, and sensor data in the opposite direction. Using HTTPS and an added custom layer of AES-CBC encryption, the streams of data remain accessible only to the user and the drone. In order to control the drone remotely, a ground control station is necessary. This simply consists of a device such as a laptop, tablet, or phone, and a common web browser such as Mozilla Firefox, Google Chrome, or Safari. This becomes a ground control station after connecting to the designated central server in the browser. This brings up a selection page that lists all the drones currently available. Clicking the swap button will set the web page up for the communication with the drone, where a map showing the location and live video will be available. The current version of the site is shown at drone.lenvoya.com, if you would like to see it. Overall, the project was quite successful, even given the setbacks of delivery times, faulty parts, and of course COVID-19. The drone flies over LTE using the onboard microcontroller and a cloud web server. Just about any device can log into the Ground Control Station web app and fly it from wherever. This includes laptops, desktops, iPads, and even phones. Live video is shown consistently, and drone location is known at all times. The microcontroller handles emergency situations through GPS log backtracking to home and soft landing. All of it has been set up to work with both commercial LTE and private General Dynamics networks. Since we have some extra time left, here are a few fun facts about the project. Over the course of the year, more than 8,000 lines of code were written in 6 different languages. 8 communication protocols were used, ranging from I2C to HTTP. In some cases, debugging these protocols on hardware was best done using LEDs. The encryption library used was built entirely by our team to the original military specifications of 128, 192, and 256-bit advanced encryption standard to ensure reliability of all data protection. The drone frames used in the final product are quite large, with the 680 Pro having a diameter of 695 centimeters and the X6 having a diameter of 1 meter. Lastly, in order to control the drone with a microcontroller, we attached a 2.4 GHz controls receiver to the digital logic analyzer to look at electrical pulses it produced under certain situations. We then modeled those pulses using the internal PWM timers on the ESP32 device.
In conclusion, the Unmanned Aircraft Secure Video Transmission over a Cellular Network project was an ambitious project to make and integrate multiple systems that allow an operator to operate a drone from anywhere as long as there's a cellular connection. Even with the setbacks, the drone was able to be completed, which we are all very excited about. This project could not have been completed without the enormous support and guidance we have received from our mentor, Claude Merrill, and our sponsors, Ernest Cholo and William Fahrenkrock.